Hi there. Today I will tell you about our work on non-reversible parallel tempering. So the setup is that we're given a distribution of interest, which is only known up to a normalization constant z. This normalization constant is difficult to compute in general, but the numerator, gamma x, can be computed pointwise. So it's a fairly standard setup in MCMC. And our goal is to approximate integrals using a law of large numbers. The standard recipe to get a law of large number for a high-dimensional problem for a given target distribution is the celebrated Metropolis Hastings algorithm. And that's an example of a reversible MCMC algorithm. However, in order to guarantee a law of large number, it's enough to use what's called non-reversible dynamics. And what's interesting with these more relaxed constraints is that indeed it's in general this could be a much larger class of algorithms. For example, in discrete state space, you can think about reversible constraints as putting n square equations or constraints, whereas non-reversible only has order n constraints. And so this is just some intuition, but this leads to the natural question whether there are probably superior algorithms in this set of non-reversible algorithms. And the answer is yes. So this has been shown in special cases. This was studied for over 20 years now. But the question that we're interested here is whether there are broadly applicable non-reversible algorithms, which are basically practically better and provably better than some kind of reversible counterpart. And what I mean here by broadly applicable is that we would like to avoid making assumptions such as X being from an Euclidean space, as many current work is in non-reversible dynamics is assuming. And this is useful to accommodate, for example, phylogenetic trees or random graphs and so on. So the answer to this question is yes, and so this is joint work with my student Saif Said and collaborators George Lidianidis and Arnaud Doucet. And in this preprint linked here, we showed that this is the case for a class of MCMC methods called parallel tempering. And moreover, the gap between reversible and non-reversible in this context is actually quite substantial. So just as a bit of background, parallel tempering is a fairly old idea now. You can think about it as a meta-algorithm, actually, which takes as input some kind of any MCMC algorithm and output another MCMC algorithm, and the transform MCMC algorithm, that's output, is often much more performant. Just let's start with the basics, so the notion of annealing. So annealing is a trick to define a continuum of distribution, pi beta, which are indexed by an annealing parameter beta from 0 to 1. A common recipe in Bayesian analysis would be to take the likelihood and exponentiate it with respect to beta. We keep the prior out in order to maintain integrability on the whole interval 0, 1. Notice that with this construction, at beta equals 0, we get only the prior, which has a very nice structure, which often allows us to sample independently and identically distributed replicates. At the other extreme of this continuum of distribution, we have beta equal 1, the posterior distribution. And assume that, note that here we make no assumption on X. So we can always define this annealing continuum, whether it's a phylogenetic tree or X, whether X is a phylogenetic tree or X is in a Euclidean space. So it's in some sense as general as any Lebesgue integral, whereas a lot of current work on non-reversible dynamics is more looking at the kind of Riemann setup where we're in a Euclidean space. So this let's sort of go over a few iterations of the parallel tempering algorithm, the standard one. Before that, let's define what will be the state space of this augmented MCMC. So it's essentially taking big N independent replica or copies of the state space of interest. I'm showing here n equals 3. And let's start with something simple where each replica lives in the real line, just for pedagogy. Now the augmented MCMC is going to explore a high-dimensional distribution with these big N copies of the state space. And the target distribution or stationary distribution of this augmented chain is simply a product of annealed distribution. So you see these pi beta as defined before. They are annealed version of the target. The target of interest is on the top, the prior is on the bottom, and those in between interpolate. And the parallel tempering algorithm will alternate between two steps. The first one is what we call local exploration, where basically for each of these big N chains separately, we are going to apply a few iterations of any MCMC algorithm that we have for each target. Except for the prior, where maybe we can get IID samples. Then we were going to attempt communication between neighbor chains. So we're, to put this in a metropolis Hastings context, we're going to have a proposal distribution which swaps the state between two neighbor chains, and then we're going to accept or reject that swap. So we're going to use that visualization for these swaps. So here the swap was accepted, so there's these green crossing arrows. Then we're going to do a second iteration of local exploration, where samples move a little bit more. And then a second communication is attempted, and again successful. And then finally, let's do one more iteration. Here we have an example where a communication step was rejected. The acceptance was less than 1, and the uniform was greater than that value. So we rejected that sample. So this summarized parallel tempering. And for the algorithm, in its reversible flavor, there's what's called a Goldilocks curse, which means that for reversible chain, adding a few parallel chains is beneficial. More increasing big N will help initially. Then at some point, adding more parallel chain will actually be harmful, and it's really a curse, and it's too bad because many users would love throwing more parallelization at hard sampling problem right now, and this is saying that for reversible parallel tempering, this is not possible. Because otherwise, PD would be very suitable to parallelization and distribution. And in the case of distribution, notice that we do not need to exchange states across the network. The different chain can exchange temperature instead of state, so it's a highly distributed algorithm. The cause of this Goldilocks curse is called a diffusive behavior, so it's well known in the literature, and informally what it says is that n chains will require in the order of n square step to carry a sample from prior to posterior, and it's not enough to offset a parallelization gain of order n. So at some point, adding more chain will actually slow down the rate at which sample go from prior to posterior. So the state of the art has been to adaptively select a number of chain big N and spacings between these chains. So these annealing parameter beta 1, beta 2 up to beta n. So see, for example, the work of Kone and Koft, Achade, Roberts, and Rosenthal, Miyazo, Geyer et al. And a representative recommendation that emerged from this body of work is that one should target an acceptance probability of around 23%. And this is motivated with an asymptotic argument that assumes that the distribution of interest is a product of D independent component and D is taken to infinity. And the optimization itself is usually approached using stochastic optimization. So our theoretical result informally states that Goldilocks curves disappear if we look at the non-reversible version of parallel tempering. What I mean by this is that with non-reversible parallel tempering, increasing the number of cores and chain never hurts, but I should emphasize that there is still a diminishing return, which I'll tell you more a bit later. Moreover, non-reversible parallel tempering probably dominates reversible parallel tempering for any given number of chains. So first, I should describe a little bit what is this discrepancy between a reversible and non-reversible version of parallel tempering. Okay, so let's start with a basic building block, which is basically based on swaps. And in a communication round, so we're going to attempt to swap as many consecutive disjoint pairs of chain as possible in parallel. So we denote the swap indices by I plus 1. So to understand the difference between reversible and non-reversible parallel tempering, we're going to call an even swap a communication round where we pick swap pairs such that I is even. And we're going to define an odd swap as picking a swap pair such that I is odd. At each communication iteration, with reversible parallel tempering, we're going to stochastically pick E or O using IID coin flips. And for the non-reversible parallel tempering, we're going to deterministically alternate between E and O. So this terminology DEO is due to Okabe et al. In 2001. So it's an algorithm that's been used in the past, but what we're adding here is to understand that it's the key difference here is a non-reversibility dynamics that's emerging, and that this non-reversibility actually opens the door to new adaptation methods for the schedule. And in fact, it's quite a surprise that the seemingly minor detail has a profound impact on the behavior of the PD algorithm. So our theoretical result is that, as I mentioned, that this Goldilocks curves disappear in non-reversible parallel tempering. And moreover, we have a second result which states that non-reversible parallel tempering probably dominates reversible parallel tempering for any given number of chains. In order to explain this, I'm going to first explain what we mean by domination. So I need to define a certain notion of optimality. So first, the setup we're going to be interested in is cases where we have access to distributed computing. So we can summon as many machines as we want. And we're going to also assume that the prior is special in that it gives us IID samples. Now imagine that the prior sample always sample a new color at each iteration, a new unique color. So you can understand a random restart with this interpretation as an iteration where the posterior chain sees a new color. So this is an example here with the visualization I introduced earlier of a purple arrow is showing the first random restart, the first time a new IID sample from the prior percolated to the posterior distribution. Now we define the restart rate as basically the fraction of MCMC iteration that are random restarts. So this quantity will be called tau, and the first result states that for non-reversible parallel tempering, the restart rate dominates reversible parallel tempering under certain conditions. And this is true for all big N, big N being the number of chain greater than 1. Moreover, for a number of chain n large enough, we have that tau for non-reversible is an increasing function of n. So it will increase to a value that's less than 1. So in this sense, there is a diminishing return in adding chains in non-reversible parallel tempering. However, this is still a large contrast with tau in the reversible setup, which will first increase and then decrease to 0 as n goes to infinity. So the key simplifying assumption that we need in order to make this, analysis is what we call efficient local exploration. So what this means is that if we have a state x beta that's distributed according to a chain at annealing temperature beta, applying the local exploration kernel will lead to log likelihoods before and after, which are at least approximately independent. And one thing to note, which is maybe a bit counterintuitive, is that it's actually more reasonable than assuming that the state themselves, x beta and y beta, are independent. So I'll show you some empirical support for this in the next slide. And empirically also, what is perhaps even more important is that the results are remarkably robust to heavy violation of the efficient local explorations. In some cases, the local exploration kernel is only doing a small Gibbs move, but if n big N is large enough, the ELE is restored for a reason that I'll talk about later. So, but here's some numerical support of this claim that the independence of the x beta is a much stronger assumption than for the likelihoods, the log likelihood applied to the x beta. So what you see here is for a Bayesian mixture model, trace plots for x beta, for a component of x beta on the first row, so namely a mean parameter for one of the cluster components. And on the second row, I show this function, the log likelihood, evaluated at a sample x beta. So because of label switching, we see here that there's a strong multimodality. So for non-reversible parallel tempering with 30 chain, we're able to jump between these two label switch. Whereas if we only use the same local exploration kernels, i.e. having only one chain, we would be stuck in one of the two modes. However, even though we have this multimodality in X, in terms of the log likelihood, it turns out that using just the local exploration kernel alone gives you a fairly good approximation of this function L of X. Now, what are the consequences of this non-asymptotic result is that it opens the door for a kind of a different direction for asymptotic analysis. So typical asymptotic regimes that are used in parallel tempering, so they would include things like letting the number of data points going to infinity, small n, or letting the number of parameter go to infinity, d, or letting the running time, i.e. the number of Monte Carlo iteration, go to infinity. So a road less traveled, at least in MCMC, is to let the number of cores available go to infinity. And arguably this is more relevant than letting the time go to infinity. So just to give you a bit more detail on the setup of this asymptotic regime that we consider. As I mentioned before, when a swap is accepted, the two machines can swap annealing parameters instead of state. And this is, for practical implementation, that's much more efficient because this has a constant cost, whereas the state could be very large. But this gives us also a perspective on the behavior of PT, where we can ask, so what is the sequence of annealing parameter that is visited by one machine? And this corresponds to basically the bold line in this figure that I've shown earlier. And now we can ask, what is the distribution over this path as big N goes to infinity? So what is interesting here is that if you do only this small modification of deterministic alternation versus stochastic alternation between even and odd swap, we get qualitatively different behavior. So for reversible parallel tempering, the weak limit when time is rescales at O n square is a diffusion, whereas for non-reversible parallel tempering, when the time is rescaled as O of n, the weak limit is a piecewise deterministic Markov process, a PDMP. So let's review a little bit what is a PDMP for completeness. So it's a stochastic process which is defined by a deterministic flow, let's call it phi, and the process will follow this deterministic behavior, and then at a random time, which is driven by an inhomogeneous Poisson process with rate lambda, it will perform a transition that's determined by a transition kernel Q. And the intuition here is that from the deterministic alternation of even and odd emerge just from the combinatorics of how these swaps are organized, a certain persistence of motion or inertia. And this will be true as long as the proposed swap is not rejected. The rejection probability for one swap goes to 1 as the number of chain goes to infinity, but there will be more and more of these proposed swaps, so essentially the inhomogeneous Poisson process will emerge from this. So when the swap is rejected, what we observe is essentially a one-dimensional bounce. So to encode this intuition, we're going to consider a PDMP with an augmented state space, where the state space Z is a pair, which is an annealing parameter beta, and a direction epsilon, which can be either +1 or -1. So essentially now, with this definition, the transition Q, when there's a jump, is essentially just a one-dimensional bounce. So we're just going to flip this direction epsilon. Now the question is, what is the bounce rate lambda? So an interpretation for the bounce rate is going to be if we normalize it, the distribution of where the rejections occur. So let's to formalize this idea, let's normalize this this intensity lambda by its integral from 0 to 1. So this is going to be called capital lambda. And by normalizing over this quantity, we get a distribution over the annealing parameter where swaps are rejected. So here's an example in an Ising model, and we see that lambda as a peak at the critical temperature of the limiting Ising model. So one interpretation of this normalization, capital lambda, is going back to this earlier result that I mentioned of this restart rate converging to a constant less than 1. Well, this constant is actually given by 1 over 2 plus 2 lambda. And moreover, this asymptotic rate can form the basis of a new schedule optimization method. So what we're going to do is we're going to estimate lambda from samples and use it to adaptively select this sequence of beta in order to maximize the restart rate. And without such adaptation, parallel tempering is not practical. And previous adaptations schemes, they are based on stochastic optimization, and we found that empirically they're slower to converge and less robust. So as a first result that came out of this analysis is a new proof for a classical result, which is that the optimal schedule is a schedule which will attain an equal acceptance rate between all chains. And at a high level, the new method to optimize this, to achieve this, is to loop over different rounds of adaptation. First, we're going to run parallel tempering and estimate lambda, And then we're going to pick a schedule so that the area under the curve lambda between chains is constant. So this is an example in the Ising model where the blue dots is an optimal schedule and green is the area under the curve lambda. So now this relies on being able to estimate lambda. And typically quantities used in the study of MCMC are difficult to estimate from the MCMC output. For example, the ESS, spectral gaps, mixing times, and so on. In contrast, lambda admits several nice estimators. So perhaps the simpler one is given by this expectation where imagine that we have a pair of chains that are independent and x beta and y beta are IID according to that target. Then lambda at annealing parameter beta is given by the expectation of this absolute value difference. I'm missing a 1/2 here. So a second method that's even more practical for estimating lambda is to use an equivalent cumulative barrier defined as big lambda beta, the integral from 0 to beta of this small lambda. And this cumulative barrier admits a simple estimator from empirical rejection rate, which is simply the sum of the rejection rates for the chains, for the pairs of chains at the left of annealing parameter beta I. So to give you some idea of what this function lambda looks like in practice, there's quite a big diversity depending on the characteristics of the problem considered. So for problems from both statistical physics and Bayesian inference, we see that there are these sort of phase transition, empirical phase transition that occur at intermediate value of between 0 and 1, which makes it very important to use adaptive schemes, data-driven adaptive schemes, rather than naive schedules such as geometric spacings. So to give you an outline of the full schedule optimization method that we derive from the second method for estimating lambda, we're going to start with an initial schedule, let's say just uniform or geometric, and run parallel tempering for small n iterations. Then we're going to compute the following cumulative swap rejection statistics. So this graph on the x-axis is the annealing parameter, and each x-axis step is a parameter spacing between two chains in the current schedule. The y-axis step is a rejection probability estimated between this pair of chain from the first n iterations. So we get that empirical if we normalize it, would be like an empirical cumulative distribution, and we fit a monotonic increasing smooth function to it. Then we're going to project the uniform grid on the y-axis through the inverse of that smooth function, and this yields an updated schedule. Then we're just going to go back to 1 using a new updated schedule and use twice as many MCMC iterations. So to give you a concrete example of what this looks like, for a Bayesian mixture model, we start with uniform spacings, and as we update, we get this interesting non-trivial schedule, which takes into account a certain phase transition that occurs when the indicator function of the label become clustered for the two cluster components. So this adaptive scheme performs well in a wide range of models. So we tried for a large range of models, from simple foundational models such as GLM and Bextor models to more complex ones such as cancer copy number calling, ODE parameter estimation, spike and slab, and a couple of phylogenetics models. And we always found that within about 10 to 12 rounds, the scheme converge to an equi-acceptance schedule. We also compare this to other schemes to optimize schedules which are based on reversible dynamics, and we found up to a factor 10 improvement in terms of effective sample size per second. To give you some example of what posterior distribution look like in that Bayesian mixture mole I talked a little bit earlier. So here on each facet is the rows show the two mixture mean components, and by label switching, these should be identical to each other, since they're the two components, mixture components, are exchangeable under both prior and posterior. And the facets rows, or columns rather, are showing different methods that are methods for exploring multimodal posterior distribution. So they include AIS, a single chain, parallel tempering based on reversible and stochastic optimization, and our method, the non-reversible parallel tempering, as well as annealed sequential Monte Carlo. So for fairness, we run all the methods using more wall clock time compared to our methods, and we see that the only method that can achieve this capture this multimodality is this sequential Monte Carlo, but only after several rejuvenation steps were performed after, which makes the running time in the order of 5 times larger than non-reversible parallel tempering. Without rejuvenation, even annealed SMC does not correctly capture the symmetry between these two parameters. This is shown also in the trace plot that MCMC methods that such as one chain or stochastic optimization, reversible parallel tempering do not capture the multimodality. We also saw the same kind of phenomenon on real-world problems involving copy number callings, where we have, to make a long story short, essentially a global parameter, which can be interpreted as like the ploidity of a certain genome, which has effect on many, a large number of chromosome-specific parameters, and really it's a great example where the exploration kernel itself is not sufficient to explore the chain, the full space, and so again the three facet here show a single MCMC method, a reversible parallel tempering scheme, and the non-reversible parallel tempering scheme, and we can see that only the non-reversible parallel tempering scheme is able to recover these two modes in that real-world problem. As a bonus application, we get as a byproduct of running this adaptive scheme an estimate of base factors, and again here we show for 16 models, and where the x-axis is the adaptation round and the y-axis is the log normalization constant estimate. We see that within about 10 rounds we get the estimate stabilized to an estimate of the log normalization constant. So if you're interested in using this for concrete data analysis, we built a probabilistic programming language with a syntax that looks like bugs or stan, and this is available at this address. There's an ID that can be used on the desktop. There's a command line interface as well as a web IDE. This is a practical scheme, so that can be used for a wide range of data analysis, Bayesian data analysis scenarios. And we have a preprint available for the non-reversible parallel tempering available at this URL here. Thanks for your time.